Welcome to this fourth video on the trigonometric circle. This one video is a bit less focused on curriculum content as the first three were, but we are going to play around a little bit with the trigonometric circle, especially with its implication with the sine rule, the cosine rule, and the area of a triangle using trigonometry. I hope it's going to help you get a wider picture of the topic. So let's briefly come back to one property that can be seen on the trigonometric circle, and that relates the sine and cosine of the angle x, as shown here, and 180 minus x. Okay, so you see these 2 points are symmetrical in the y-axis. This means that the cosine of 180 minus x, which is an obtuse angle, is going to be negative and inverse to the cosine of x. These two angles, nonetheless, have the same sign, which has a positive value. This is what we need to keep in mind for what's coming next, so let's first have a look at the area of a triangle. So if you've studied this topic, you must have seen that the area of any triangle can be given by half of b times c times the sine of angle A. And one question that you can rightfully ask yourself is, what happens if this A here becomes an obtuse angle? So let's see what would happen. We are going to keep the lengths C and B unchanged, so the line segment C is not going to move, but the point C here is going to move along the circle, making sure that this line segment B has the same length as any other that we're going to draw. To do this, we are going to have a look at this specific triangle here, where the green line here is parallel to the side C, and we have a new triangle that is like this, and the angle A is now right here. So first of all, we need to work quickly with the angles because the two lines are parallel here. You see that this angle A is alternate to this one, so they're going to be equal. Here we have an isosceles triangle because we have two radii on the same circle. So this angle again is equal to angle A. And finally, if we extend this line, again we have corresponding angles on parallel lines. So the four blue angles here are equal. You can see then that this angle here is therefore 180 degrees minus A, because A is to be found here, and these two angles are on a straight line. And let's now compare the area of this triangle here with the area of the triangle there. You can notice that because the two lines here and there are parallel, the perpendicular distance in between these two lines is constant. So this means that the height here is equal to the height there. So this means that these two triangles have the same base here, if we choose C as the base, and they have the same corresponding height, so the areas, they must be the same. Okay, so if we use the formula to write the area of this triangle here, we are going to find half of BC sine of 180 degrees minus A. So this clearly shows that these two things here, these two signs, they must be equal to basically ensure that the area of these two triangles here are going to be the same, and that the formula is valid for acute and obtuse angles as well. So this is totally consistent with what we've seen on the trigonometric circle, and that the properties that were shown on this circle are nicely consistent with this formula for the area of a triangle. Let's now have a look at the sine rule. So if I look at this triangle, the sine rule allows me to write that sine C over C is equal to sine B over B. So again, let's keep the angle B constant, the length B constant, and the length C constant. So C is going to move on the circle, making sure that B remains the same. There is only one position possible for C to meet this condition if you don't want to change the angle B, and that's if you extend this line here and if you work with this triangle here in green. you can check that here this length is still B, this length is still C, and that this angle B hasn't changed either. You can notice that again we have an isosceles triangle, so the two angles shown in blue here must be the same. And if you look at what's happening at point C here, you can see that these two angles should be 180 degrees minus C. So this basically means that if in an exercise you are given C and B and the angle B, and you ask to work out the angle C in this triangle, well, you don't really know in which triangle you're going to work. It might be the first one here, it might as well be the second one right there. And therefore, you have two possible values for the angle that you're supposed to work out. So if you look for the missing value in this formula here, you might as well find the sine of the angle C if you're working in a small triangle, or the sine of 180 degrees minus C if you're working in a large triangle. Okay, this one is the obtuse angle triangle, and for this one it's the acute angle right there that you're looking for. And well, again, you see that everything is consistent with the trigonometric circle, because these three values being given here, you have no choice regarding the fourth one that you're looking for here. And these two things, even if you don't know which one you're working out really, they have the same value. If you check again the trigonometric circle, the sine of these two angles has to be the same. So this means that you will need a little bit more information if you have a question like this to actually decide whether you're looking for an obtuse angle or an acute angle. Let's now have a look at the last thing that I wanted to talk about in this video, which is the cosine rule. What's happening with the cosine rule is probably slightly easier to understand. In this triangle, we can write that a squared is equal to b squared plus c squared minus 2bc cosine of the angle A. Angle A being right there. And what we want to understand now is what happens if we change this A here, and this A only, for a 180 minus A. What we want to understand now is what happens if we change this angle A for the obtuse angle 180 degrees minus A. To do so, we can extend the line AB just like this, and if we repeat angle A right there, we see that the angle 180 minus A appears right there. So the new triangle with sides C and B and the new long side A right there still follows the cosine rule as shown here. Now this A is a 180 minus A. And we see that it makes sense that the cosine of this obtuse angle is negative because it will turn this term here as a positive term, making the side A longer than what it was when the angle here was acute. You see, A was much shorter than it is now when this angle has been made obtuse. And here there is one last thing that is interesting to look at. If you make this angle A 90 degrees, so here your triangle will be like this, it will be a right angle triangle. You see that this term here becomes 0, and that what is left here is Pythagoras theorem. We'll get A squared is equal to B squared plus C squared. I hope I managed to trigger some interest for these extensions of the sine and cosine rule. And for Key Stage 5 students, there is the 5th video coming about the relationship of sine and cosine of some more special angles.